All right, let's dive into some fascinating research. On a topic I think we're all too familiar with these days, hurricanes.
Yeah.
Specifically, we're going to explore how effective sand dunes really are
Okay.
at protecting coastal communities. When a major hurricane hits, like Hurricane Michael, you shared some research
Right.
detailing a study that uses this XBeach model
Yeah.
to analyze Hurricane Michael's impact on Mexico Beach, Florida. I'm really curious to unpack this together.
Yeah, it's a great choice for a deep dive, I think. We all know the damage that hurricanes can inflict, but quantifying the protective role of sand dunes
Yeah.
is really crucial for coastal management, especially as we see more intense storms these days. This study uses XBeach to simulate how hurricane-generated waves behave
Oh.
as they travel from the open ocean, across the beach, over the dunes, and finally into the community behind them.
Before we get into the model itself,
Sure.
can you kind of paint a picture of just how powerful Hurricane Michael was
Oh, absolutely.
and the extent of the damage in Mexico Beach?
Hurricane Michael was a Category 5 monster
Wow.
with sustained wind speeds reaching 72 meters per second.
Oh my gosh.
The devastation in Mexico Beach was catastrophic.
Yeah.
Widespread destruction of buildings and infrastructure. Figure 1 in the paper really drives home the sheer force of this storm.
It's a stark reminder of what we're up against. So let's talk about this XBeach model.
Okay.
I'm familiar with some numerical modeling in general,
Sure.
but I'm really keen to hear how XBeach specifically simulates these complex coastal processes during a hurricane.
Yeah, so XBeach is a really versatile tool that allows researchers to simulate a wide range of coastal processes, including wave transformation, overtopping, and dune erosion. In this study, they used 2 versions of XBeach: XBNH, the non-hydrostatic model, and XBSB, the hydrostatic model.
I understand that hydrostatic and non-hydrostatic models have different strengths and weaknesses.
Yeah.
Can you elaborate on the differences and why the researchers chose to use both?
Yeah, the key difference lies in how they handle shortwave dynamics. So those are those rapid fluctuations in water level caused by waves. XBNH, being non-hydrostatic, directly simulates these short waves, which is crucial for accurate erosion predictions.
Yeah.
However, this accuracy comes at a computational cost. XBSB, the hydrostatic model, averages out those short waves, making it computationally more efficient, but less precise, particularly when modeling erosion.
So it's a trade-off between capturing those really fine details
Exactly.
of the wave behavior and the computational resources.
Yeah.
Given the focus on dune erosion in this study,
Right.
it makes sense that they opted for the higher fidelity of XBNH.
Exactly.
But they didn't just run the model blindly, right? They validated it using real-world data from Hurricane Michael.
Precisely. The researchers were very rigorous in their validation process. They compared the model's predictions with several sets of observations, high watermarks, meticulously collected by the USGS after the storm, time series of significant wave heights and storm surge levels from the USGS gauge that thankfully survived the hurricane.
Oh, wow.
And pre- and post-hurricane LiDAR data to assess changes in dune and beach profiles.
Using LiDAR data is an excellent way to capture those fine-scale changes in dune morphology. So how did the models perform when compared to these real-world observations? Did they accurately capture the extent of dune erosion?
Yeah, the results, which are detailed in section 5.3 of the paper, show that XBNH consistently outperformed XBSB, particularly in capturing those complex patterns of dune erosion. And this highlights the importance of accounting for those shortwave dynamics, especially when studying those erosion processes.
That makes sense. The short waves would play a really significant role in scouring the dune face and transporting sediment.
Absolutely.
Now let's get to the heart of the matter.
Okay.
How effective were the dunes at attenuating wave energy during the hurricane?
That's where figures 12 through 15 become really insightful. They provide a visual step-by-step representation of wave propagation. Across the beach and over the dunes, at different stages of the storm surge, what's striking is the clear reduction in wave height as the waves cross that dune crest.
So we're literally seeing the dunes acting as a barrier, absorbing and dissipating wave energy before it reaches the community behind them. Can you walk us through what's happening in these figures in a bit more detail?
Of course. Figure 12 shows the wave field during that lower rising surge phase, and you can see that even at this early stage, the dunes are effectively reducing wave heights.
Okay.
As the storm surge increases, depicted in Figure 13.
Right.
The wave heights increase, but the dunes continue to attenuate a significant portion of that wave energy.
It's fascinating to see this dynamic interplay between the rising water levels, the increasingly powerful waves, and the resilient yet eroding dunes. What happens as the surge reaches its peak?
Figure 14 shows the wave field at the peak surge. Here, the dunes are being heavily eroded.
Oh, wow.
And while they still provide some attenuation, their effectiveness is definitely reduced compared to the earlier stages. The overtopping flows are also much more pronounced, with large volumes of water flowing over that dune crest.
That's a critical point. It seems the dunes provide the most protection during those initial stages of the surge. And as erosion intensifies, their protective capacity diminishes. What about during the receding surge phase?
Figure 15 depicts this final phase. You can see that while the wave heights are decreasing, the dunes have been significantly reshaped by the erosion. And their ability to attenuate waves is further reduced. And this highlights that long-term impact of hurricane-induced dune erosion on coastal vulnerability.
So it's not just about the immediate impact during the storm, but also the lasting effects on the dune system and its future ability to protect the coast. These visualizations really drive home the dynamic nature of this process. But is there a way to quantify this attenuation effect?
Absolutely.
To put a number on how much wave energy the dunes are actually absorbing?
The researchers went beyond that visual analysis and quantified the wave attenuation using data from their model simulations. Table 10 in the paper presents some striking findings. During the upper rising surge phase, when the dunes were relatively intact, they observed a remarkable 91% reduction in wave height.
That's an incredible level of protection.
It is.
A 91% reduction means that the dunes are effectively knocking down almost all of the wave energy before it even reaches the community.
It's a testament to the power of natural defenses. However, as we saw in the figures, this protection comes at a cost. The dunes erode, and their effectiveness diminishes over time. At that peak surge, for example, the attenuation dropped to 35%.
So there's a trade-off. Protection in the early stages. But increasing vulnerability as the storm progresses and the erosion intensifies. This raises a lot of questions about how we can best manage and enhance these natural barriers.
It certainly does, and that's where the real-world implications of this research come into play.
Well, this has been an incredibly insightful dive into the dynamics of wave attenuation.
Thank you.
And the crucial role that sand dunes play. I'm really eager to continue exploring the broader implications of this research.
Me too.
So let's pick up this conversation in part 2.
Sounds great. Welcome back. As we continue exploring this research on dune attenuation, I'm struck by the potential for using these insights to design more effective coastal defenses.
Yeah, I agree. It's fascinating to think about how we can apply these findings to protect coastal communities, especially with the increasing intensity of hurricanes, due to climate change.
Yeah, one of the key takeaways for me is the importance of considering the entire storm surge cycle, not just the peak surge, when designing those coastal protection measures.
That's an excellent point. The research showed that dunes provide the most protection during the early stages of the surge, when they are still relatively intact.
Exactly. So strategies like beach nourishment, where sand is added to the beach to bolster the dunes, could be most effective if implemented proactively before a storm hits.
That makes sense. By reinforcing the dunes before they are subjected to significant erosion, we could potentially enhance their ability to attenuate wave energy throughout the storm.
Precisely. And this research also highlights the need to account for the long-term impacts of dune erosion. Even if dunes survive a storm, their altered morphology could make them more vulnerable to future events.
So it's not just about surviving a single storm, it's about ensuring the long-term resilience of the dune system, which is essential for protecting the communities behind them.
Absolutely. And this is where tools like XBeach become incredibly valuable. We can use them to simulate different storm scenarios and assess the effectiveness of various coastal protection strategies.
It's like having a virtual laboratory for the coast, where we can test out different approaches and identify the most effective solutions.
Precisely. Now, shifting gears a bit, I'm curious about the specific types of waves that impact the dunes. Does the shape of the wave, whether it's a plunging breaker or a spilling wave, influence erosion patterns?
That's a great question. It intuitively feels like the way a wave breaks would affect how it interacts with the dune, but I'd love to hear your perspective.
Well, the study itself touches upon this in Table 9, where they calculate something called the breaker-type coefficient. This coefficient essentially describes the steepness and energy of a wave right before it breaks.
So a plunging wave, which is that classic towering wave that curls over and crashes down with force, would likely have a higher breaker-type coefficient than a spilling wave, which kind of rolls gently onto the shore.
Exactly. And we can hypothesize that plunging waves, with their concentrated energy release, might cause more localized erosion at the base of the dune, while spilling waves might distribute their energy over a wider area.
That makes sense. So understanding the specific types of waves that are likely to hit a particular coastline could be crucial for predicting erosion patterns and designing effective protective measures.
Precisely. And this is where the limitations of the hydrostatic model become evident. It simply cannot capture those fine-scale differences in wave-breaking dynamics that could significantly influence dune erosion.
Which again reinforces the need for the more computationally demanding but accurate non-hydrostatic model, XBNH, to really understand these nuanced processes.
Absolutely. And as computational power continues to increase, we can expect models like XBNH to become even more sophisticated, providing even richer insights into these complex coastal processes.
Speaking of complex processes, we've been focusing on natural dunes. But what about artificial dunes? Can they provide similar levels of protection?
That's a fascinating question, and I believe this research can inform the design and optimization of artificial dunes.
So by understanding how natural dunes attenuate wave energy, we can apply those principles to engineer more effective artificial barriers.
Exactly. Imagine using XBeach to test different artificial dune designs and configurations in a virtual environment. We could assess their performance under various storm conditions and identify the most effective shapes, sizes, and materials.
That's a brilliant idea.
Yeah.
It's like a virtual wind tunnel for dunes, allowing us to optimize their design before investing in costly construction projects.
And this brings us back to the idea of using XBeach as a predictive tool, not just for analyzing past events, but for anticipating future ones.
I'm really intrigued by this concept. Can you elaborate on how we could use XBeach for predictive purposes?
Imagine being able to simulate a hurricane's potential impact on a specific coastline, taking into account factors like the storm's track, intensity, wave characteristics, and the local topography.
We could essentially create a forecast of how the coastline might be affected, including dune erosion, overtopping, and potential flooding.
Precisely. This information would be incredibly valuable for coastal managers and emergency responders, allowing them to make more informed decisions about evacuation orders, resource allocation, and long-term mitigation strategies.
It would be like having a crystal ball for hurricane impacts, giving us a glimpse into the future and empowering us to take proactive steps.
It's a powerful concept. And as models like XBeach continue to evolve, we can expect their predictive capabilities to become even more refined.
This all leads to a broader point about the importance of data collection and validation in these studies. The researchers in this paper were meticulous in their efforts to validate their models using real-world observations.
Absolutely. Validation is the cornerstone of any sound scientific study. And the researchers here went above and beyond, using multiple sources of data to confirm that their models accurately captured the dynamics of Hurricane Michael's impact.
They compared the model predictions with high water marks, waves and surge measurements, and even detailed dune profiles before and after the storm. It's impressive.
It is, and it gives us confidence that these models are providing a realistic representation of what happened during the hurricane, and by extension, that they can be trusted to guide future coastal management decisions.
So we've covered a lot of ground here, from the power of the XBeach model to the nuances of wave dynamics and dune erosion, and the potential for using these insights to design more effective coastal defenses. But before we wrap up, I want to touch on a crucial aspect, the human element.
Absolutely. Behind all the data, equations, and simulations are real people living in coastal communities facing the very real threat of hurricanes.
This research isn't just an academic exercise. It's about providing tools and knowledge that can help protect lives and livelihoods.
Indeed. And as we delve deeper into this topic, it's crucial to remember that our ultimate goal is to create more resilient coastal communities.
This research has provided us with valuable insights into how dunes attenuate wave energy, how they erode, and how we can potentially enhance their protective capabilities.
It's a reminder that knowledge is power, and that by harnessing the tools of science and engineering, we can face the challenges of a changing climate with greater confidence.
Well, we've certainly had a thought-provoking discussion about the dynamics of hurricane wave attenuation and the role of dunes in coastal protection.
It's been a fascinating exploration, and I'm excited to continue this conversation in our final part.
I agree. There's still much more to uncover. So join us for part 3, where we'll delve into some even more intriguing aspects of this research. Welcome back to our deep dive into hurricane wave attenuation. We've explored the fascinating world of XBeach modeling, delved into the nuances of wave dynamics, and even touched upon the human element in all of this. But there's one more intriguing aspect I want to explore before we wrap up.
I'm all ears. What's caught your attention?
Well, I'm curious about the shape of the dunes themselves. We've talked about their size and how they erode, but could the actual geometry of a dune, like its shape, impact its effectiveness as a wave attenuator?
That's a great question, and one that researchers are actively investigating. Intuitively, it makes sense that the dune's shape would play a role. You know, a steep, narrow dune might cause a wave to break more violently, concentrating erosive forces at its base.
Right, while a wider, more gently sloping dune might distribute the wave's energy over a larger area, potentially leading to less severe erosion.
Exactly. It's like the difference between a head-on collision and a glancing blow, you know?
Oh.
The shape of the dune could determine how that wave's energy is absorbed and dissipated.
So it's not just about having dunes, it's about having the right kind of dunes.
Precisely. And this is where XBeach can be such a powerful tool. We can use it to create like virtual dunes of various shapes and sizes, subjecting them to virtual hurricanes to see how their geometry affects wave attenuation and those erosion patterns.
It's like a virtual wind tunnel for dunes, helping us design the most effective shapes for coastal protection.
Exactly. And this knowledge could then be applied to both natural and artificial dune systems. Imagine using this information to guide beach nourishment projects, ensuring that the added sand is sculpted into the most resilient dune configurations.
This brings us back to the broader theme of using XBeach as a predictive tool, not just for understanding past events, but for shaping the future of coastal management.
I couldn't agree more. The ability to simulate future hurricane scenarios, taking into account projected sea level rise, changes in storm intensity, and the evolving morphology of the coastline would be invaluable for coastal communities worldwide.
It would allow us to move beyond reactive measures and embrace a more proactive, adaptive approach to coastal protection.
Imagine a world where coastal communities have access to detailed, localized hurricane impact forecasts. They could use this information to optimize evacuation plans, prioritize infrastructure investments, and make more informed decisions about development and land use.
It would revolutionize how we prepare for and respond to these powerful storms.
And it's not just about the technical aspects. This research also underscores the importance of collaboration between scientists, engineers, policymakers, and the communities themselves.
It's about bringing everyone to the table, sharing knowledge, resources, and perspectives to create a more resilient future for our coasts.
And at the heart of it all is a deep respect for the power of nature and a recognition that our best defense often lies in working with natural processes.
The dunes have been protecting our coasts for millennia. We just need to learn from them and support their ability to continue doing so.
So as we wrap up this deep dive, let's carry with us a sense of wonder, a thirst for knowledge, and a commitment to protecting these invaluable coastal ecosystems.
This research has been a reminder that even amidst the destructive force of hurricanes, there is beauty, resilience, and a story of adaptation waiting to be uncovered.
It's a story that underscores the interconnectedness of our planet and the profound impact our actions have on the natural world.
I want to thank you for joining us on this incredible journey of discovery and for sharing your expertise on this fascinating subject.
It's been my pleasure, and I hope this deep dive has sparked a sense of curiosity and a desire to learn more about the world around us.
That's a wrap on this episode of The Deep Dive. Thanks for listening.